You may be wondering why I'm speaking to you in a darkened room lit only by one garish bare bulb. Well, what I'd like to do is to demonstrate diffraction gratings with the help of the bulb. I actually have several diffraction gratings that have different numbers of lines or slits or scratches per millimeter. And the reason I'm using this particular bulb is because it is, first off, it's not frosted, and the filament is more or less in a straight line vertically. So it acts like its own slit for a spectrograph. And so the light that comes to the diffraction grating will only be coming from this one direction. So what I'm going to do is I'm going to come around, I'm going to put behind the camera, and I'm going to put diffraction gratings in front of the lens. Now I have several diffraction gratings. This one, here it is, and what I'm going to do is I'm going to bring it right up to the lens, and you can see to the left of the light bulb, you can see a spectrum, the brighter of the two, and if you look further to the left, you will see a fainter spectrum that is more spread out. It's fainter, but it's more spread out. So generally diffraction gratings will produce what's called a first order, that's the first one to the left of the light bulb, and then a second order that is more spread out. So that's 550 lines per millimeter. This one here is 750 lines per millimeter. And you can see that the first order spectrum is very bright. In fact, the camera really isn't capturing the colors very well. Ignore that spectrum kind of bouncing around, the faint one bouncing around at the bottom. We're getting some reflections between the lens and the diffraction grating. But the first order is so bright that, again, the camera is not really recording the colors very well. But if you look off to the left, about the left third of the frame, you can see the second order spectrum. I can even pivot here a little bit so you can see the whole thing. So more spread out than the first order. Notice that the red light is always the wavelength, always the color that is furthest from the light bulb or the source or the slit. And lastly, the third diffraction grating, this one has 1,000 lines per millimeter. So there's the first order spectrum. And you can see it's more spread out. Again, ignore that reflection at the bottom. And here is the second order spectrum, really spread out. By the way, if you see those lines, either vertical or horizontal, don't think that those are absorption lines. Those are just either artifacts from the little holders inside the light bulb that's holding the filament, or fingerprints and whatnot on the diffraction gratings. We are not seeing any absorption lines in this demonstration. These are the diffraction gratings that I used for the demonstration. This is the 750 lines per millimeter. This one has 1,000 lines per millimeter. This has 550 lines per millimeter. These are transmission gratings. The light goes through them. They're transparent, but then they have the scratches, the slits, we say, that are parallel to each other. And like I said, 550 lines per millimeter of width on this one. These are not expensive. These are manufactured for like novelty glasses and for science classes. This, on the other hand, is a professional grade diffraction grating that could be used in a research instrument. And it is a reflection grating. That is, it's not transparent. Light doesn't go through it. It acts like a mirror, but the mirror has hundreds of slits carved into the surface per millimeter, and that causes diffraction interference resulting in a spectrum.